Hey there, in this video I want to talk about eigenvalues and eigenvectors. So consider the matrix equation, ax equals x prime. In physics what this would represent is some kind of transformation. A changes vector x into a new vector x prime. So for example, A could be a rotation, written as a rotation matrix that rotates x and makes a new vector x prime. And so for any square matrix A, so it's an n by n matrix, you're going to have n special values called the eigenvectors. So these are special x's that when you apply the transformation to them, you get the same x back, maybe just scaled by a constant. So this would be special cases where ax equals lambda x, where the x that this works for is called an eigenvector. And the lambda here is the eigenvalue that goes along with that eigenvector. So in the case of a rotation, that would be the rotation axis. So if you try to rotate a vector that sits on the rotation axis, it doesn't change. That vector just spins in place. And so that would be the rotation axis itself is the eigenvector, and the eigenvalue, if you didn't change it at all, would be 1. You didn't do any scaling at all. So in general, we're looking for n eigenvalues and n eigenvectors, and these can be useful because those eigenvectors in a more abstract sort of sense can be thought of as the best sort of coordinates for your system, the best way to describe things. So like in the case of a rotation, describing rotations about different rotation axes is a good way to describe the rotation. So let's look at an example here. Let's say that the matrix A, we'll just keep it 2 by 2, make this fast, is 1, 2, 2, 1. And that rotation, or that matrix, doesn't have to be a rotation matrix. That matrix has eigenvectors. You've probably learned how to do these problems by hand, but let's skipping that part, jumping ahead. What you're going to find for those eigenvectors is 1 on square root 2, negative 1, 1 is the first eigenvector, and the second one is 1 on root 2, 1, 1. And then by convention, we normalize these things. So that 1 on root 2 guarantees that this vector has a length 1. In the most general sense, eigenvectors don't have to be normalized, but in physics, we do that by convention. And if you have eigenvectors, you're going to have eigenvalues. And so the eigenvalues that go along with these eigenvectors end up being negative 1 for the first and 3 for the second. And so we sort of split this apart into pieces, but we can also write just a single matrix equation that contains all of the eigenvalues and eigenvectors in it. So let's write that equation as A times V equals V times D. And so V here stores the eigenvectors. Specifically, the eigenvectors are the columns. And D here stores the eigenvalues, and they're going to be sitting along the diagonal. And all the other elements of D would be 0. So let's just check. In the problem we just did here, A is 1, 2, 2, 1. I want to multiply that by a matrix of the eigenvectors, and so both of those have a 1 on root 2. The first one over here is negative 1, 1. The second one is 1, 1. So that would be the eigenvectors down the columns. And then that is supposed to be equal to that same matrix V. Let's just copy that over. Multiplied by a matrix D that has the eigenvalues down the diagonal. So negative 1, 3, everything else being 0. And so if we check if those two sides are equal, the 1 on root 2 would cancel out. No, you can't just cancel out entire matrices because they're left multiplied versus right multiplied here. But we'd carry out the matrix multiplication, and I'm going to get 1, 3, negative 1, 3 on the left, and on the right I'm going to get 1, 3, negative 1, 3. So sure enough, if you work this out, you'll find that, yeah, okay, this works. So you can express all your eigenvectors and values in a single matrix equation. And that's really going to be the key to the next part. So now let's look at another piece to this puzzle. Let's look at what happens. We're going to jump over the notebook, and we're going to look at what happens here when we play around a little bit. So we're going to try something here that's going to reveal at least one of the eigenvectors for the matrix 1, 2, 2, 1. Let's start by typing that out. 2 and 2, 1. And what I'm going to do here is I'm going to repeatedly matrix multiply A with a column vector. And I'm going to start with a column vector that is not one of the eigenvalues, or eigenvectors, I mean. So let's do something simple like 1, 0. And then we're just going to do this over and over and over again. So I'm going to use a for loop for I in range. We'll try 10 times. I'm going to redefine x as a multiply x. So doing the matrix multiplication here gives me a new column vector, and then we're going to use that in the next step. And then each time through, let's print this out. So we're going to print x, and if I'm looking for something like eigenvectors, the typical thing to do is normalize them. So we can divide by its norm, same thing as its magnitude. And linalg is the SciPy linalg. I already have that imported here. Okay, so it looks good. Let's see what happens. Oh, I forgot in. Oh, silly me. All right, so for I in range, of course. So here we go. We are starting through. We started with 1, 0, and then after the first iteration, we've got something entirely different. We keep iterating. Look at what we're getting down here at the bottom, 0.707. That is 1 on root 2. And hey, what do you know? 1 on root 2, 1 on root 2, that is one of the eigenvectors. So strangely enough, maybe not really strange, but maybe surprisingly, if you keep doing this iteration, you get an eigenvector. Why? Why? It's because eigenvectors are special. They are values that aren't changed by transformations. They aren't changed by the transformation A. So any set of transformations keeps changing you until you get stuck at one of these points called stationary point. Now the thing is, this equation here has 2 eigenvectors. And so how do we find the other one? We need to do something a little bit fancier. But we can't necessarily just guess other values. I mean, I suppose if we guessed the other eigenvector would be okay. But typically what happens is you end up stuck on the eigenvector with the largest eigenvalue. And so this one has the larger eigenvalue, and that's why we get stuck on it. We're going to talk about another way that we can find all of the eigenvectors in eigenvalues coming up back over where I am able to handwrite stuff. Okay, so what we saw there is we just repeatedly applied the same matrix over and over and over again, and what do you know? We found an eigenvector. Because we found one of them. So wouldn't it be great if we could find all of them? And sure enough, there is a way to do that. It's called Qr Decomposition. So as it happens, any square matrix can be decomposed, that is split into 2 different matrices called Q and R, where Q here is orthogonal. And just a reminder what that means. Orthogonal means that Q transpose is equal to Q inverse. And R here is upper triangular. So with the details deferred for now, let's look at the recipe that will let us find all the eigenvectors and all the eigenvalues. So step 0, just to get us started here, is we need to pick some starting values for V, which is going to hold our eigenvectors. We're going to go with the identity matrix, so that's just 1 down the diagonal. And then we're going to do a decomposition, turning A into Q times R, and there's a linear algebra way to do this. And then for step 2, we're going to calculate a new value for A by setting it equal to R times Q. Notice we switched the order there. So it should be kind of like the original, that's owing to the Q being orthogonal here, but it won't be exactly the original. And we've got to do the same thing to V, so we're going to replace V with V times Q. And then step 3 is we're going to go back to step 1, and we're just going to keep doing this over and over and over again. And as we do this, what we're going to discover is that A starts to change. The diagonal of A is going to survive, but the numbers are going to start to approach the eigenvalues, and the off-diagonal elements of A are going to decline to 0. And then the columns of V are going to become the eigenvectors. Let's just write that down. So A turns into what we called D a little while ago. And then V becomes what it's supposed to be. There tends to be a lot of symmetry with eigenvectors. You can really get burned here if you forget that it's the columns. It's not the rows, but it's the columns that contain the eigenvectors. So let's go try this out in Python. To save ourselves a bunch of time, there's actually some built-in methods that will do the Qr decomposition for us. So we'll use that as sort of a quick way to get the Qr decomposition. We're going to try out this routine and see what it actually does to our matrix. We'll see how it works. And then we'll look at the built-in routines that already do all that for us. So we don't have to code this recipe. It's already done for us, but just so you know how it works behind the scenes. So let's try out Qr decomposition and see how it works for us. I want to do this, we have to apply the Qr decomposition repeatedly, and so I think a nice way to do that would be to have it draw its result and then erase, draw again, erase, draw again. This would be a good place to use display from IPython. Also be a good place to use time to give us a little bit of time to look at the results so it doesn't just fly through it. So I'm going to import those things. Okay, so I've got display and time at the ready. And we need to define some values V and A to match our Qr decomposition. V needs to start at least as the identity matrix. We're going to do a 2x2 problem, so identity 2 will give me a 2x2 identity matrix. And A is the array we've been using. So that would be 1, 2, and 2, 1. And now we're going to do repeatedly Qr decomposition. So I'm going to do this in a for loop. Let's do it 12 times. Seems to work pretty well. And we're going to run through the steps of Qr decomposition. And then what I want to do is clear the display. That'll be a clear output. We want to set weight equals to true. And then what I'm going to do is print A, print a blank line, and we're going to print V, and then we're going to wait a little bit. Let's wait 1 second. So this whole for loop will take just slightly more than 12 seconds. Okay, now up here, I want to run through the steps of the actual Qr decomposition. So to get Q and R, I mean, there is a way to do this, and in the textbook, it walks you through it. But for the purpose of this code, I just want to show you that it works. So we're going to let Python calculate the Qr decomposition for us. There's a function called Qr that does that. And now we're going to do the update step. So we're going to let A be R matrix multiply Q. We're going to let V be V matrix multiply Q. And that's it. Those 3 lines right there are Qr decomposition for us. So each time we calculate a new Qr decomposition, and then we multiply to update A and V. And then we're going to print A and V as we go. The whole thing should take about 12 seconds. So as it runs through this, and this actually happens really fast, but we're built in a time delay, what we're going to see here is the diagonals up here in A become the eigenvalues, 3 and -1. The off diagonals are getting smaller and smaller. You're done when these are small enough, so you pick some tolerance. So in this case, 1 part in a million seems pretty good. And then the columns here of V, those become the eigenvectors. Be careful, it is the columns. So we had 1 on root 2, 1 on root 2, and then over here, -1 on root 2, 1 on root 2. All right, so great, we can find eigenvectors and eigenvalues. Do you really have to code this thing every time? Well, no, of course not. There's already a function that'll do it for us. I just wanted to show you how it worked. And the name of the function is eig. So this is in SciPy's version of linalg. And we've got eig. Actually, we've got a couple things. We've got eig and then eig with an H. We're usually going to use the one with an H. The H here stands for Hermitian. So meaning A is a Hermitian matrix, and usually in physics they are. It means that it's kind of like a Hermitian matrix is a lot like a symmetric matrix. Instead of being identical around the diagonal, though, it's a complex conjugate around the diagonal. And most matrix equations you run into in physics are Hermitian. If it's not a Hermitian matrix, don't use this function. Because what it does is, to be more efficient, it only looks at the diagonal and one side of it. It doesn't look at the other side. And so if you had a non-Hermitian matrix and you put it into this function, it would effectively ignore half the values and give you a nonsense result. All right, so what we're going to do here is, I already defined A up here. Let's just copy that code, start fresh, because we have modified A in the previous cell. So reset A here, and then the outputs of this are going to be the eigenvalues in the eigenvectors. So let's call those variables eigenvalues, eigenvectors. You see I'm using tuple unpacking to get both of these out at the same time. And then we're going to feed this matrix A, and that's it. It's a one-liner. We can print the eigenvalues. Hardest part really is spelling eigen. Print the eigenvalues, print a blank line, print the eigenvectors. Okay, and if we run that, our eigenvalues are -1 and 3. You know, these don't really come in any particular order, so it happened to give me a different order than the code we wrote up here, but those are the two eigenvalues, and the eigenvectors are, once again, the columns. Be really careful about that. They are not the rows, they are the columns. So for -1 here, we have -1 on root 2, 1 on root 2, and then over here, 1 on root 2, 1 on root 2. This is maybe not the greatest example, because if you read across the rows, you would say, hey, I got the same eigenvectors. But that's not always the case. They're not always like super symmetric like this. So be really careful. It is the columns. There is a cousin of this that gives you just the eigenvalues. And that's called let's start out typing out eigenvalues. So eigenvals or eigenvals H. There's even banded and tridiagonal versions of these, but let's look at eigenvals H, again assuming we have a Hermitian matrix A. In that case, our output is just the eigenvalues. Let's just let it print the whole raw output. And we'll see, it's just going to give me a single array, just the eigenvalues. Why would you want to use this? Well, if you had a really big matrix, this is a lot faster than calculating both the eigenvalues and the eigenvectors, so it's an efficiency thing. All right, so I think this video has gone quite long enough, but we have looked at how you can calculate eigenvalue problems using Python.